Welcome to the Free Library of Philadelphia. My name is Laura Kovacs, and I'm honored to introduce Dava Sobel and Priya Natarajan. Renowned for her work in deciphering the mysteries of dark matter and dark energy, Yale astrophysicist Priya Natarajan is a recipient of Guggenheim and Harvard fellowships, the India Abroad Foundation's Face of the Future Award, and a member of the Royal Astronomical Society. Exploring everything from the Big Bang to the possibility of other universes, her book, Mapping the Heavens, is a tour of the cosmological findings that have changed our modern understanding of the universe. Dava Sobel is a former science reporter for the New York Times and the author of 5 books, including Longitude and Galileo's Daughter. Her many honors include the National Science Board's prestigious Individual Public Service Award, and she even had an asteroid, number 30935, named for her. In The Glass Universe, she recounts the story of the ladies who worked at the Harvard College Observatory in the late 19th and early 20th centuries, who read the secrets of the skies on glass photographic plates, discovering new worlds in the heavens while forever altering the scientific world below. Ladies and gentlemen, please join me in first welcoming Priya Natarajan to the stage.
First of all, I want to say what a pleasure and a privilege and an honor it is to have this opportunity to talk to you all about this book. And it is a particular privilege to be speaking along with Dava because the women whose work she's going to be talking about today are the pioneers who have opened the doors and the corridors for people like me who have come along a couple of hundred years later. So very grateful to you for unearthing that history. And what I wanted to do today was to talk to you a little bit about the motivation for why I wrote the book, and then sort of take you through a brief journey of the history of the idea of dark matter. With one of the interests that I have is of the human side of science, the psychological side of science. So what I'll try to do is to briefly describe some of the characters that have been key in the dark matter story, but then I will rapidly move on to show you how far we've come. And although we've learned a lot, there's a lot more to learn, a lot more to discover. There's room for many young scientists who are going to come well after me to really discover the wonders of the universe. So I've been very interested from a young age in trying to understand why some radical ideas in science catch fire and why some of them don't actually make it to being accepted. And in particular, after I started working in cosmology, so from the ring side, I had my own ideas, and I noticed the reception that some of these ideas had. And I often wondered, what is it? Was it something intellectual about that idea that caused a prolonged delay before it was accepted? And I know the delay here, I should tell you how spoiled we are, right? So I've been in the field for about 15 years. So this is a new era of science where you propose a new idea, and within 5 to 10 years, it can be tested, validated, or discarded, right? So this is the new pace, and for the impatient generation. But so what I've been interested in is the intellectual pushback that as scientists, we are trained to have an open mind. That's part and parcel of our training, that you have to be open to new ideas and changing your point of view with the preponderance of new evidence and data. So that is very much part of our training. But what I found from my own encounter, and of course historically looking just at even the last 100 years, that scientists themselves often resist because they're human. Science is a human activity. And if an idea or its implications are particularly disorienting, then scientists really push back. And it was that process that I was most interested in. How the scientific community, in particular cosmologists, have pushed back, and yet some of these ideas have gained traction. And although these ideas are at sort of somewhat comfortable and uncomfortable stages, as I'll show you, for example, with the concept of dark matter. And of course, the other motivation for writing this book was the worry about the rampant disbelief in science and the scientific method, and the fact that reasoned analysis of data, which is the only way we can make sense of the world, is something that's being contested today, and particularly in the United States, which to me has been a very deep conflict, because this is the country, people like me who grew up in India came here because this country is at the forefront of science and technology, right? To come here and to encounter this was deeply disorienting. So I have a very personal take on why this is, and I differ slightly from many of my physicist colleagues, which is I think that the key reason the curious public is not able to accept science so easily is there are two features of science which are particularly attractive to scientists but are hard for others to understand who are not involved in the process. That is the provisionality, the contingency of science, the fact that with new data and new evidence, you have to change your mind. You have to be open, and so there's a revision. You are constantly revising your understanding, but you're honing it, you're deepening it, and you're refining it. And the other concept is that of uncertainty. So part of what I wanted to do in the book was to demystify the process of science and how science is done, and to bring into sharper focus the human side of science, the individual personal ambitions, the rivalries, and sort of there's a very sanitized account of science, as though sort of these people in lab coats sort of extracting truths from nature in a very objective way. And I think in a way I wanted to debunk that and show the complexity. The complexity with a purpose, and the purpose being that this is a deeply human activity. And I think the other thing that was very tempting to show is the current excitement. The reason it is so exciting to be alive, to be doing science now, is because there's a grand convergence. There's sort of a confluence of our theoretical ideas in most subjects, and definitely in cosmology, especially in the last 100 years. And particularly the last 20 years have been special because the ideas, the maturity, the scientific maturity of theoretical ideas, and the instruments, the sophisticated instruments that we now have to test those ideas, and the computers that we have to analyze, test, and model, there has been a real alignment in that sophistication. So it used to be 30 years ago, people, theoretical astrophysicists or cosmologists could have any kind of theory, and there wasn't enough data to substantiate one or the other. So you could sit on the fence and write a paper one day saying this and the opposite another day, because you didn't have the data to really differentiate. But that's not the case now. And as I started out, we are in a moment where within 10 years, any new idea that you propose can actually be tested. But let me take you through what I think is a sort of a brief journey of the intellectual tone of my book, what I was trying to do there. And so, as I mentioned, I'm deeply interested in the process of science, the practice of science, and how that has changed. And of course, this does include facets that Dava will be talking about. I mean, who gets to do science and how they get to do science. The fact that women are now included, and yet, not quite there in terms of where we think the participation of women scientists and their recognition should be. But also the science is very global. It's very international now. And I think that's also been an interesting development in the last 100 years or so. And I have been very, very intrigued from childhood with maps, and maps both celestial and terrestrial. And I tend to think of our knowledge map and how that's advancing. So I use it both literally as well as metaphorically throughout my book. I map ideas into maps, because then it's easy to talk about the morphing of ideas by looking at the maps that get updated, remade, redrawn, and so on. And in particularly, if you want to talk a little bit about the history of ideas, it turns out that before you had peer-reviewed scientific articles, it was really maps that showed you how the worldview was shifting with new ideas. And so I want to start by just giving you sort of a few interesting sort of vignettes as to how human beings have forever wanted to map. The minute we could look up at the night sky, we've been wanting to make sense of the night sky. But we wanted to make sense of it in a very different way from what we understand today, which is a scientific explanation. And I think the ancients, and even up to the 1300s, 1400s, down to after Copernicus, they were not really looking for causes quite yet. It was really Kepler who came along, and we started looking for sets of principles and laws. People were looking for coincidences and connections between the celestial and the terrestrial, because they couldn't understand, they couldn't make sense of causation. So one of the earliest representations of the cosmos is this wonderful copper disk called the Nebra disk. And all I want you to notice here is the year, 2000 BCE. It's just remarkable, right? It's the sun as the Pleiades cluster. And then my favorite ancient people, the Mesopotamians, they were inveterate charters of the sky. And what you see here, cuneiform has now been decoded. So what we know that these are the positions, documented positions of the planet Venus. So this should already make you gasp, as it made me, because they already knew the difference between a star and a planet. And this is 7th century BC, right? So let's jump really way ahead. And this is one of my favorite illuminated maps from the 1300s, where once again, I want to drive home the point that, there were sort of representations of the cosmos. There was a fixed orb of stars. They were trying to make sense of night and day and the seasons. But the idea of causation, the fact that there could be principles, was not quite there. So you see these two angels turning the crank. And I really love that. And then, the adjudication of ideas, right? And it turns out this is a theme that repeats even today. If you have an idea that's extremely radical, then it's very hard to accept it from the get-go. And often there's sort of a halfway house negotiated kind of understanding. You sort of have to step into that, and then you can make the final leap. And there's a history for that. And here you see Copernicus reordered the solar system and moved the pivot from the Earth to the sun. But that was a radical idea, and many, like Riccioli here, and Brahe, liked sort of a halfway house model, where basically the Earth might move around the sun, but all the other planets move around the Earth. So sort of keep a little bit of both, right? And and in here you see the muse of Urania, the muse of astronomy. And I think one other thing I want you to notice is that in 1604 to 1607, Galileo had already repurposed the spyglass as a telescope and pointed it upward. So here the one-eyed Argus is sort of holding the telescope. Notice that it has now made an appearance. And you see Ptolemy sitting there with his beard, kind of his model has been discarded, right? So you see him sitting there pathetically. So as I said, what I now want to do is to really take you forward and show you the work that has been done, that has been enabled by the Harvard computers, by the astrophysicist traditions of astrophysicists, stellar celestial mechanics workers over the last 200 to 300 years. It gave us all the tools to get to where we are today. So, and this is really remarkable, because in 1914, we did not know about the existence of any other galaxies. Okay, and 1914, it's not that long ago, about 100 years ago. And now we know there are billions and billions of galaxies out there, and we talk about the existence of potential multiple universes. So there's been real leaps of understanding. So I'm going to take you through a very quick tour of one radical idea, and the history of that idea, and where we are at with for now. So first of all, we've sorted out the timeline for the universe. So we know that the universe is about 13.8 billion years old. We know when structures started to assemble in the universe and when galaxies like ours formed. And we also know that in the driving seat of all of this is dark matter. Dark matter structures the universe. And ordinary matter, the stuff that we are made of that's in the periodic table, is less than 4% of the universe, the matter content of the universe. So we know the composition of the universe. It's a very peculiar universe, an uncomfortable kind of composition, because the bulk of the energy content of the universe is dark energy. This is a force, a repulsive force that countervails gravity, that causes the accelerating expansion of the universe. So today we know the universe is not just expanding, but actually the expansion is accelerating. And that little sliver, that's us, that 4%, that blue cyan sliver. So it's really quite remarkable that we are here and we have the human cognitive capacity to have figured all of this out. I mean, I find myself in awe all the time. So I just wanted to briefly mention the kind of analysis that I do in the book, which is I take a whole bunch of ideas. I've taken the discovery of the expansion of the universe, dark matter, black holes, dark energy, other exoplanets, possibility of other universes, and I compare and contrast what is different about each of these ideas. Each is radical in its own way. So for example, I'll be talking mostly today about dark matter. And dark matter is an invisible entity, and we know that dark matter exists because of the effects that it exerts on matter around it, on the motions of stars and galaxies and so on. And it was empirically found. So we found data and evidence that suggested the presence of dark matter. By contrast, one of the other radical ideas is that of black holes. And black holes were found as a mathematical solution to Einstein's field equation, an exact solution when Einstein didn't expect one, and a very peculiar one at that. And it took a long time for black holes to actually become real, to understand that they were real astrophysical objects that corresponded to that mathematical solution. Took a long time, that journey. So it was sort of the inverse of what happened with dark matter. So let me quickly take you through what our state-of-the-art understanding is and show you historically some of the milestones in our understanding of dark matter. So the evidence really comes from the impact, because dark matter is matter. It does not emit, reflect, or absorb light, but what it does do is deflect light, as we will see in a moment. So there's independent of whether you believe in Newton's gravity or Einstein's gravity, Einstein's model theory of general relativity upended Newton's notion of gravity. It refined it and profoundly reconceptualized it. Either way you want to view the universe, you still find that there's a need for dark matter. So I'll show you that's why the idea of dark matter is so compelling. And it's not like ether that's going to go away, or phlogiston or miasma, these medieval fluids that all went away. So the first empirical discovery of dark matter was made by Fritz Zwicky, who was a cantankerous astronomer at Caltech. And what he did, what he looked at is, this is a coma cluster of galaxies. So these are about 1,000 galaxies that are actually held by the invisible grip of dark matter that you don't see in that image. So he measured the speeds of these galaxies, about 12 of them, and he found that they were whizzing around much faster. They would not be held if they were moving this fast if the only matter was what you saw in terms of the stars that you see in that image. And so he proposed the idea. And then Einstein's theory of general relativity predicts that any lump of matter in the universe would deflect light. And that is because the universe is this four-dimensional sheet of fabric of space-time. And what mass is, what he conceptualized mass is what causes dips, divots, or potholes in this fabric of space-time. And just to remind you, there's nothing above space-time or nothing below. So we are all confined, we're all living in this sheet, and therefore light has to travel from distant sources to us, and light will sample each and every little pothole on its way to us. So the source, the shape of a galaxy from which the light is emitted, is deeply distorted by the time it reaches us. But so there are two different techniques, as I mentioned. Either you go via Newton or via Einstein, you find this compelling evidence, incontrovertible evidence for dark matter. So one of the pioneers, much like, sadly, much like the pioneering women that Dava is going to be telling us about, is Vera Rubin. And I say much like pioneering women is because she has received credit, but we've all been in the astronomical community waiting for the ultimate accolade for her, and it hasn't happened yet. She hasn't been awarded the Nobel Prize yet. So in the 1970s, Vera Rubin and two of her colleagues, Kent Ford and Thonard, noticed they were measuring the speeds of stars in galaxies. And what they found was the expectation was that it should look like that red curve that you see. Because if all you see is what is there, then the gravity of that sort of falling off as you see starlight oozing away. And so the speeds of stars as you go from the center outward should fall because you're running out of matter as you go further out. But what they measured was the white curve. And that might not seem as radical at the outside, but let me just bring you closer to home and show you how radical that is. So if you look at the solar system and you look at the speeds of the planets around the sun, you find that as you go further away from the sun, which is the main gravitating body, the most massive body in the solar system, this is called the rotation curve, the speeds slow down. And sorry, it's my blind spot. Pluto is still a planet for me. I'm not able to give that one up. So you notice that the velocities, the speeds actually decline as you go further out. That's because much of the source of the gravity center is in the sun. And so this is by contrast. This is what is different in galaxies. If you measure the speeds of stars from the center outward of a spiral galaxy, you see there in blue is the top view. You are finding that the stars are moving. They're starting out slow, they're capping out at a maximum value, and then they stay flat. So literally, it looks like there's some matter that we don't see that's holding up the galaxy out at very large radius. So this was the first sort of empirical evidence to bring the contrast to you more sharply for the existence of dark matter. So there is close to 90% more matter that is providing the gravity to hold up and explain the speeds of stars that are measured. And this was found in the 1970s. But Vera Rubin and collaborators actually did not present the results for a long time. They sat on it. It was too radical. And so they were waiting to get more and more data. And finally, they decided that, okay, although they didn't mention the word dark matter in the first publications, they later finally published it. So this is our current conception of a galaxy, including our own, that what you see as the stars are just the tip of the iceberg, and much of the matter is unseen, and it's dark matter. So let's come to Einstein's view. If we live and adopt his worldview, then he showed that the presence of matter should bend light, as I mentioned, the potholes in time. And so the ultimate test, the first test of his theory of general relativity was the prediction that during a solar eclipse, because the sun, when the sun, moon, and earth line up, then because of the deflection of light from stars that you can see their actual positions, during a solar eclipse, they don't appear to be where they are. They're displaced from their actual positions because the sun produces a deep pothole and light has to traverse that pothole to reach us. And now when there isn't an alignment, when it's no longer a solar eclipse, you can find out what the real positions are. So Einstein's theory predicts that difference between the real and the apparent position. So that was the test. And that's what really made Einstein famous overnight in his theory. So this is a sort of snazzier rendition of this, showing you the pothole in space-time that is gridded, and the stretching is showing you that there's a deep pothole. And this is an object that's called cluster of galaxies. There are about 1,000 galaxies of the same things that Zwicky studied. And what you see is light from a distant galaxy out there. The paths are, these are all possible light paths. Light is coming uniformly, but just shown you some of the paths that are going to be hugely deflected. So because light is confined to travel on space-time, it actually follows the pothole, and different light rays have different travel times, so you end up seeing a distorted image of that original galaxy. This is another schematic of that. So this is an example from the Hubble Space Telescope. This is a real image. And what you see is a single galaxy. That little blue blob is really what's there, but it gets distorted because of the presence of an intervening galaxy with a huge dark matter halo, rather like the ones that Vera Rubin found. And the presence of dark matter in that lenses or distorts the shape of that little blob into this huge arc. And so these are seen, and so the work that people like me do are sort of really break this up. When you see this image, to actually back out what dark matter, what matter was along the line of sight that caused all the potholes. So we're sort of basically mapping potholes. And I was telling my 10-year-old nephew, I was trying to explain to him, and I said, well, I kind of map potholes. He said, that sounds very boring indeed, And then I said, no, actually it isn't, because, where they live near Delhi, the potholes are never filled, right? So there are new potholes every time. So I keep telling him, it's very exciting work because you always find new potholes. So now the shape and the distribution of dark matter impacts how much bending you see. So when things line up perfectly, so if dark matter was a nice spherical blob, as it is, then you would see the kind of stretching that I just showed you, if it was very spherical. But if it was ellipsoidal, so a slightly different shape, then you would see a different set of sort of deformation. So we can actually do this mapping. And in fact, one incredible thing is that if you can think of light rays as tubes, you can imagine that there are tubes that go through sort of a deep pothole, and they actually get split. So you end up seeing two images where, in fact, there's only one real galaxy. So you see multiple images, okay? And that's actually seen. Now, if dark matter were actually granular and distributed as little blobs, so what you see on the accompanying right-hand side are real Hubble Space Telescope images, which correspond to each of these cases. So in fact, dark matter, the distribution, spatial distribution, is really quite complicated. So this is an animation just showing you that what you see in red, shaded in red, is the pothole. You're looking down on the pothole. And what you are seeing are the distortions that are caused in a background screen of galaxies, which were all originally circular. So you see this plethora of shapes. So this is what we do, because most dark matter is smeared everywhere in the universe, but lightly almost everywhere. But it's lumped in very few places, these places that are clusters. So we know the undistorted shapes of galaxies. And looking at these distorted regions, we can back out how much dark matter is. So remember I told you that, these images can get you get multiple images where there's a single galaxy. So here you see a single galaxy that is multiply imaged into 5. And so they're the same galaxy, and the way we know that, because remember, all astronomical objects have a fingerprint, they have a spectrum. So if you go out and measure the spectra of these objects, they're identical. So we know that they're actually just images of the same object. So this poster child, prior to the Brangelina split, I used to call this the Brad Pitt and Angelina Jolie cluster. It was over-photographed, like overused, whatever, but it has these dramatic lensing effects that you can see highly distorted background galaxies. You can even pick them out by eye, those red. And what you see in the fuzzy yellow ones are galaxies that are part of the cluster that is doing the lensing. So these are the galaxies that belong and that are causing the deep pothole to start with. So the distant ones, the ones behind, are the ones that have been stretched out. So you may ask, well, why this sort of obsession with wanting to map these distortions? So this is a simulation from one of my colleagues of a small patch of the universe. So this is all dark matter. It's mocked up to look like light. So what you are seeing is this dark matter we have inferred has very peculiar properties. It's collisionless. It doesn't collide. It has no pressure. So two dark matter particles, as you'll see, when they come close, the only force they feel is the tug of gravity. And so they eventually merge. So this is the formation of structure in the universe. It's hierarchical. Small things form first, and then they lump up. And you're seeing a cluster like the one that I just showed you the Hubble image of, how it forms. So what I want you to see here is how granular the dark matter distribution is. And remember, we don't know the nature of dark matter, right? So one of the things we've been trying to do, and the work that's motivated my own personal work, is looking and mapping the granularity of dark matter at sort of as finely as is possible given the data. And that's because here are two different simulations where the only thing that has changed is the nature of dark matter. And notice one is much smoother and the other one is very, very clumpy. So we're trying to look at patches of the universe and figure out which kind of dark matter to get a clue to the nature of dark matter. So let me just quickly show you, to wrap up, what we actually, so you take an image like this, and you analyze it. So this is looking at the pothole that's generated by this cluster. And what you see is the bunny rabbit in yellow is the region of sky. When you look through, everything that is behind the bunny rabbit, within the body of the bunny rabbit, will be multiply imaged. The light rays will be dramatically split behind that. And so this is what I do. This is a dark matter map. This is the recovery of the lumps of dark matter in that cluster. And you can see that there's sort of a smooth component, and then there's a lot of different clumps. And this is the deepest image ever taken of a cluster of galaxies by the Hubble Space Telescope. It's a new project called the Hubble Frontier Fields Project. And this is just hot off the press. And what I'm showing you on the left-hand side in blue is the reconstructed dark matter that you don't see. And on the left-hand side is the Hubble Space Telescope image. So, and right now, and this is a similar rendition to what I showed you. So it's a very, very clumpy, so it looks like the dark matter now is sort of this cold, collisionless component. To wrap up, you may say, have we found dark matter? So one of the embarrassing things is that we haven't actually found dark matter. We don't know what that particle is. And it might be that, we're not quite looking at the right places. There was a claim about 15 years ago of one detection by one experiment, but that's not accepted by most scientists. So there's now finally replications of this experiment are happening around the world. And so we should know something in in a couple of years. So I'll just wrap up with this last slide. You may say, what is really going on here? So what are we doing now with searches of dark matter, right? So we've documented the sky, we've analyzed the sky, we have a theory, and what are we doing now? We are confronting the most refined, sophisticated version of the theory with deeper and better observations. And we're looking for gaps. And the reason is that the history of astronomy shows us that gaps come in two flavors. One are the benign gaps, the gaps like the distortion, the deviation in the orbit of Uranus from Newton's prediction in our solar system, which suggested the presence of another gravitating body, Neptune. So this is how Neptune was found, from the wobble in Uranus's orbit that it generated. And this was done by this French mathematician, Urbain Le Verrier. So Neptune was discovered. Newton's laws remained intact. Similarly, there was an anomaly in Mercury's orbit. And Urbain Le Verrier suggested the same solution. He said, I think there's another planet between the sun and Mercury, called it Vulcan. People tried to look for it, and there is no Vulcan. And what was needed then was a complete reformulation of Newton's theory. So Einstein's theory of general relativity explains the precession of the perihelion of Mercury. So when you find a disagreement between a theoretical expectation and data, you don't know whether you are in the Neptune model or whether it's pointing the way forward to a brand new theory. We do know that Einstein's theory is incomplete at the moment. So we are all, people like me, are looking to find these gaps. And so in the book, I recount the journey of this kind of, showing you how the idea developed. And I focus a lot more on the controversies than I have done here, because I was very tempted to show you the latest results. So I'll just very quickly read one small bit from the book to connect up to Dava's talk, which really shows you that the work that was done about 200 years ago with photographic plates, no computers yet, with women at the Harvard College Observatory measuring the brightnesses of stars on these plates, trying to pick out, looking at plates that were taken at different times, looking at variability, and trying to glean, and arrived at incredible sort of new principles, and how that actually enabled a lot of the science that I have. I mean, it's really set the stage for everything that I've been showing you. Hubble decided to tackle the challenge of measuring distances to nebulae. Using Leavitt, this is Henrietta Swan Leavitt, using Leavitt's method, he began to look for more Cepheids. These are variable stars, and she managed to find a correlation that connected their variability, and we could use their variability to determine the distance, how far they were. This took many long, lonely nights of observing, with the help of an assistant sitting still on a platform next to the instrument mounted on the 100-inch mirror and tracking stars. So the work that Hubble did, which unmoored the universe, would not have been possible without Henrietta Swan Leavitt's discoveries. So at this point, I'll just stop, and I will let Dava tell us the story of the human computers. Thank you very much for your attention.
Ladies and gentlemen, Dava Sobel.
And I do want to point out Vera Rubin in this cover slide at a very young age in the lower right here, Philadelphia native. And it's really great to be here with a bona fide woman astronomer to talk about this story. This picture appears in Priya's book, and it dates to a time when computer was a job description, because the first women who worked at the Harvard College Observatory, like astronomical computers everywhere, were involved in helping map the stars, establish their positions, because astronomy was really in the service of navigation at that time. And these are some of the calculations they did. So you're looking at the stars through the atmosphere, which is distorting, and the Earth is moving through space, which creates other kinds of distortion. And all these things have to be worked out mathematically to get an accurate map. And the earliest women doing this, there were men computers too, but at Harvard, it was easy to just rope in the wives, sisters, and daughters of the resident astronomers and teach them how to do this work. The director who took over in 1877 was a very young man, Edward Pickering, and very broad-minded, forward-thinking. He found women already working at the observatory when he got there, and so he had no problem hiring others as the need arose. And he was a big proponent of higher education for women, which was questionable at the time because there was concern that college actually injured girls and made it difficult for them to bear children. So this was the observatory, very beautiful wooden building, very little of which remains today, but the dome of the big telescope is still there, and the building without the dome was the director's residence. And this is what was under the big dome, a 15-inch telescope that was a gift from the people of Boston. And there's Pickering sitting in the chair. And he was really a physicist, and there was some concern that as a physicist, he wasn't really fit to run the observatory. And sure enough, as soon as he got there, he wanted to move away from just mapping the stars, tracing the orbits of comets, and get into the physics of the stars. Why are they of different brightness? And what are they made of? And how do they work? Those were the questions he was interested in. And none of that was known at the start of this story. And by the end of it, a few decades later, just about everything was known. So it's a happy story. And the observatory got no money from the college, the university. But Pickering was a very charming fellow and was able to attract money for research. This couple, Anna Palmer Draper and her husband, Dr. Henry Draper, had worked together for about 15 years. She became his assistant. And even though he was trained as a medical doctor, he was a brilliant amateur astronomer. And because he was an amateur, he was free to do whatever he wanted. And so he was interested in the spectra of the stars. Priya mentioned how the spectra are the key ID marks, the fingerprints of the objects. And he wanted to photograph the spectra. He was the first person who was able to do that. So I jotted a note while Priya was speaking because she talked about an important alignment of different kinds of technology, and that's exactly what happened here. So photography was new. People weren't sure it was really applicable to astronomy, but Pickering was convinced it was, that he had seen the future. He had seen the way to pull stars out of the heavens, make them appear on a photographic plate, even stars that couldn't be seen through the most powerful telescopes, because photography, unlike the human eye, enabled light to accumulate over time. So he could run some exposures for 20 minutes, an hour, 2 hours, and stars no one had ever seen before would show up. So the Drapers were all set to devote their lives to this project, give up medicine. She was independently wealthy, and they were just going to do this big project. And right at that moment, he got sick and died. He was 45 years old. And she desperately wanted to see his dream realized and tried for a while to move the work forward herself with a few assistants. But in the end, she decided to just give her money to Pickering and let him do the project, and it would be done in her husband's name. So this is what a spectrum looks like. This is a textbook example of a spectrum. So you get this rainbow effect and the dark absorption lines along the spectrum. But photography was not yet color photography, and they looked more like this. This was a gross enlargement. Most of the plates looked like this. So Pickering wanted to photograph hundreds, thousands at a time with a prism at the object and the light gathering end of the telescope, and then turn over to the women who worked for him the job of looking at these little tiny smears and separating them into categories to try to parse what the different types of stars were. That black circle is a penny, just to give you some idea of scale. So now that photographs were accumulating, more women were required to analyze the information content of the photographs. And there's Pickering at the back, and Mrs. Fleming standing. She was one of his early hires. She had come to the observatory, to the residence, as a maid, because as a pregnant woman with her husband having disappeared, she was desperate for work, and he immediately recognized her intelligence and moved her into the observatory and taught her to be a computer. And then she went home to have her baby and came back to have a real job at the observatory, where she created the first Henry Draper catalog, analyzing 10,000 stars by their spectra and making a preliminary classification system. She went on to become the first woman at Harvard to hold a university title as curator of astronomical photographs. Here she is in a close-up view. Here's another young woman, Antonia Mori, who was a niece of Henry Draper, and she had gone to Vassar College, where Vera Rubin also attended school, and Vera Rubin went there because of that formidable lady at the telescope, who was Maria Mitchell, and discovered a comet in 1847 and became world famous. She was only about 30 years old at the time. And so when Matthew Vassar formed Vassar College, he invited her to come and teach astronomy. And Miss Mori had 8 semesters of astronomy with Maria Mitchell, so she was really prepared to work at the observatory. And she developed her own classification system, which was much more complicated than Mrs. Fleming's. But this lady, this is Annie Jump Cannon, and she was able to take the best of those two systems and juggle them and come out with something that was so effective that it's still in use today. And when she arrived in 1896, she became the first woman to actually make her own observations with the telescope. Before that, it had seemed unseemly to have a woman out in the dark at the telescope with the men during the night, or all kinds of worries about what the cold would do to them. But she was really prepared. She was a Wellesley graduate. She had studied with one of Pickering's former students. And this lovely painting is from a children's book about her called Annie Jump Cannon, Astronomer, by Carol Gerber. And the illustrations are by Christina Wald. So this is a typical plate used by Miss Cannon. She'd have to look at it, number all the stars, and then go back over it and just call out the numbers and her designations to a partner who wrote down what she said. And definitely not something that just anybody could do. One of the great resources for me in telling a story about so many women and looking for a way to distinguish one nerdy lady from another. Fortunately, Miss Cannon kept diaries her whole life, and this is what they look like. There are boxes of them in the Harvard archives. And I learned to read her terrible handwriting, and she kept them up till just weeks before her death. To photograph the whole sky, Pickering had to send an emissary to the southern hemisphere and find a place to set up a telescope so that they could include the entire sky. From Cambridge, they could see maybe half the stars. They needed another observatory. So this was their first very rudimentary establishment on something they called Mount Harvard. And then they found almost permanent headquarters near the town of Arequipa, Peru. And they were in the shadow of a dormant volcano, which later proved to be not dormant. And this was the giant telescope that Pickering wanted for the Southern Observatory. And fortunately, he found another heiress, in addition to Mrs. Draper, who was giving him the equivalent of the observatory's entire annual operating budget every year out of her own funds. This telescope was paid for by Catherine Wolfe Bruce, who just wrote him a check for $50,000. And this is a picnic in Peru. Bailey knew he was going to be there for years, so he brought along his wife, who is the pleasant-looking woman right next to me, and their child, who was about 3 years old. And she helped him work. She did a lot of the meteorology observations, and she also helped with the astronomy. And Bailey was really interested in globular clusters. I really love astronomers' names for things. You know, dark matter, Big Bang, black hole, globular cluster. You don't have to think about what it might be. There it is. So on the right is a distant view, and on the left, a partial close-up. And one of their challenges was to just count the number of stars in these objects. So they would actually rule graph paper on a sheet of glass and put that sheet over the glass plates. And from that big telescope, those plates were 11 inches by 17 inches. And then they would look at each little square through a magnifying loop that had crosshairs in it. And sometimes his count didn't agree with her count, and they averaged. And of course, at the middle, they really couldn't count them at all. Oh, and then after counting, figuring out the relative brightness and how the brightness changed over time. So this is Henrietta Leavitt, about whom we've heard something, who was looking at those big pictures from the southern hemisphere, and she was looking especially at this object. So there's a globular cluster over at the far side, but then this is the small Magellanic Cloud, and she was looking at variable stars in there and noticing that the brightest ones took the longest time to go through their cycle. And since she figured all of these stars were roughly the same distance from Earth, the brighter ones must really be brighter. It wasn't a function of distance. And so she came up with this correlation, which was and remains to this day foundational in measuring distances across space. So one of the first things that came out of it was the distance to this object. And after that, the extent of our galaxy. And Hubble, Shapley, Hubble figured out there were more galaxies than just ours. But Harlow Shapley, who took over from, after Pickering died, took over as director of the observatory, used Miss Leavitt's stars to calculate the size of the Milky Way and to realize that the sun was nowhere near the center. And that really pleased him, and he loved saying things like, man is not such a big chicken. You know, we're just peripheral. And now we know we're barely 4% of the visible material in the universe. But so at the time, he said man was not such a big chicken. And chickens were not all that interesting to him, but ants really were. And he got interested in ants while he was working at Mount Wilson and studied them over years and wrote several scientific papers, published papers about ants. And so I just wish he could have seen this Charlie Hankin cartoon, which is missing its caption. So it's like one of those new New Yorker contests where you... But I'm going to tell you what it said. Kind of makes you feel small, doesn't it? And here he is. I should have shown him first, but Shapley really believed that his gigantic Milky Way was the full extent of the universe, and he was mighty upset when Hubble wrote to him and said, I've used Miss Leavitt's stars to show that those little spiral things that you thought were part of the Milky Way are actually Milky Ways of their own, much farther away. And Shapley loved having all these women at the observatory. He used to say that that work could be calculated in girl hours, and if it was a really big job, there were kilo girl hours. And one of the first things he did was to establish a program in graduate level astronomy education, because he felt if there had been such a program in place, Harvard could have hired a new director from within the ranks. They wouldn't have had to import him from California. And the only money he had for graduate student fellowships was new fellowship money donated by yet another heiress to support young women to come and work at Harvard for a year and learn the practices there, and then go on to a job in another observatory, such as Yerkes or the Lick Observatory in California. And he turned that money into the graduate student fellowships. So the only graduate students he could bring in had to be women. And this is the first crop of graduate students. So the big picture is Margaret Harwood. She was the first beneficiary of one of these fellowships, and she wound up being hired as the permanent director at the Nantucket Observatory, where the Lydia Swain Henchman, who was the donor of these scholarships, lived and was a cousin of Maria Mitchell's. At the top here is Adelaide Ames, who came to Harvard for her master's degree, and below her Cecilia Payne was the second student, and she stayed on for a PhD, and hers was the first PhD in astronomy awarded at Harvard. And in the course of doing her research, she noticed that hydrogen, she was studying the spectra, looking at these glass plates, and she was trying to get the relative composition of the stars, and noticing that hydrogen was about 1 million times more prevalent than anything else, which seemed really against all expectations. And she was advised not to say that too loudly, but just to kind of just present what she had found and say that it was probably a spurious result. But it got a lot of attention. And even though it was counter to everyone's expectations, astronomers were willing to really look at it. And it took only about 4 years for everyone to say, you know what, it really is all hydrogen and helium. So here they all are in a picture that suggests that they were maybe not taken seriously. But they really were. They were really always given credit for what they did. Pickering nominated them for prizes. They were members of foreign astronomical societies as well as the American Astronomical Society. And the work they did was really important. Astronomers have known their names all along. And Annie Cannon was especially famous in her lifetime, and soon after, she was featured in Wonder Woman comic book as one of a real-life Wonder Woman. And that is still going on. This is from a new website called Rejected Princesses. Women who are too awesome, awful, or off-putting to be featured in a kid's movie. So this is Annie, and there's Pickering down there holding the ladder for her. I don't know how many of you saw the original Cosmos series that Carl Sagan did in the 1970s. He was a huge influence on me. I'm ever grateful to him. And the series was remade recently by the original writers with a new host, Neil Tyson. And an entire episode was devoted to the Harvard women. And as a result of that, 2 new plays are being written about them. And there's a web series coming also called Insignificant. Great pun there. Yes, they're even Lego figures, and you can get this design on a T-shirt if you are so inclined. So here's Henrietta Leavitt looking at the variable stars on the glass plate, and then Annie Jump Cannon with her stellar classification, and Cecilia Payne pointing out the prevalence of hydrogen and helium. And this is a painting. You'll recognize the Small Magellanic Cloud. This is a young woman named Leah Halloran, who also got fascinated by these women and is working on a major art installation called Your Body is a Space That Sees, which will open in Delaware next spring. And she paints images from the plates and then uses them as a negative. And these are cyanotypes that are produced in sunlight. So she loves the fact that there's another star involved in the production. And these are huge images, about 6 feet square. And there's still a lot of material at Harvard. Several boxes of things recently turned up in a repository. So there's lots more work to be done, all kinds of crowdsourcing opportunities. The plates, the 500,000 plates, which still live in the brick building that was built especially for them at Harvard, are all being digitized because they are still in use. And it'll be a lot better when astronomers don't have to travel to Harvard or handle the fragile glass to use the plates. If anybody who's interested in volunteering, let me know. I will tell you the contact. This is one of my favorite pictures of them, and I'll end with this.